Hello, everyone. I'm Professor Nguyen, John Nguyen. Welcome to chemistry. But today we're doing organic chemistry, all right? And these are the simplest one. These are hydrocarbons. Guess why we call them hydrocarbons? It's because they only contain carbons and hydrogens. Okay. Carbons are the backbone of any organic compound structure. Okay. All right, let's start out with functional groups. Functional group is a group of atoms that has special physical and chemical properties. All right. The nice thing about it is it doesn't matter what kind of compound we're dealing with, as long as it has the same group of atoms known as functional group. They have similar or the same physical and chemical properties. Okay. So that's the nice thing about that. So we just focus it on anything other than carbons or hydrogens, any bonds other than single bonds. For example, like double bonds. Okay, and we call this alkene. That's the name, the class name. Functional group is the structure. The name is alkene. Just like you look at a pen, that's the structure of a pen, and the pen is the name. Okay, so every structure we have a name. An example, like ethene or ethylene. Now, notice carbon has 4 bonds. Double count is 2. So you see carbon right here has 4. 1, 2, 3, 4. If we have nothing to be bonded to carbon, nothing else other than hydrogen, then we'll put hydrogens. Okay, hydrogen, hydrogens. And that in that case, and that's what we got, ethene. It's the simplest alkene, okay, we can have. All right, so double bond, alkene. If you see a triple bond, and that means we only need another bond to make it 4. Triple count is 3 for carbon, okay? That's the structure or functional group. Every time you see any molecules that has that triple bond, we call that alkyne, okay? Ethyl or acetylene is an example, the simplest alkyne we can have. All right, now how about we have 3 double bonds in an enclosed structure, hexagon, right, with 3 alternating, double, single, double, single, double, single. Now we can have whatever we want other than that. If we don't have, then we just put hydrogens, okay? Now the nice thing about this kind of structure, we don't have to show hydrogens. They are secretly there, okay? That's in the case of that, we just ignore those, okay? And that's benzene. Now this is the structure. That's an example. Benzene is specific name. What is the name of this functional group or the class name? It's a class, okay? That will be aromatic. All right. Now, if we have, and like I said, any atoms other than carbon or hydrogens, that will be, there's a chance for that to be a functional group, okay? Meaning special structure. So let's say that's an X, and X can be fluorine, or we actually call fluoro, chloro, bromo, and iodo, okay, end with O. In that case, these are halogens. That's what we call them, halide, okay? That is a functional group, halide. Just one single atoms make a difference, okay? For example, chloromethane, all right? Now, if that special one is actually 2, OH, it could be an atom, it could be a group of atoms, OH, but that's what we're focusing on. Anything with OH, any organic compound with OH. That is alcohol. For example, methanol, ethanol, propanol. They all alcohol. They all have special physical and chemical properties. Okay. Now, all right. So we have more. This is just one example. Now that's our job, to be able to look at the molecules, identify special atom or special group of atoms, any double bond, triple bond, those are special bond, and be able to tell what's the name of that functional group, not the whole molecules. That's a different topics. All right, that's naming organic compound. All right. Now we got this oxygens, but notice that there's no hydrogens next to it, just by itself. Both sides bonded to carbon. Okay, like methyl on both sides. We call dimethyl ether. It's known as an ether functional group. And ether has special physical and chemical property, like very, very flammable, very reactive, Okay, now these are the one that's really cool. Monophosphate, later in biochemistry, we're going to run into phosphate. Monophosphate, phosphate is PO4, 1 oxygen, 2, 3, 4. Diphosphate, that's 2 of them. And also triphosphate, like ATP. The reason why we call ATP in biology, A is adenosine and T is tri and P is for phosphate, triphosphate. That's the energy molecules. Okay, amine is a compound with nitrogens. Notice that, the nitrogens. It can have 2 hydrogens. This nitrogen, if you notice, it has to have 3 bonds. Remember, carbon 4, 1, 2, 3, 4. Nitrogen has to have 3 bonds and a lone pair of electrons. Now, double bond carries 2, just like carbon. Okay, well, if it has all single bond, 3 bonds, we call that amine. For example, methylamine. Imine is not very popular, but it happens with double bond. Okay, double bonded nitrogens. That's called imine. That's the name of the functional group. Nitrile is a triple bond nitrogens. So you can see from single, double, triple, that's nitrile, like ethane nitrile, triple bond. Sulfur, that's called thiol. And if there's no hydrogen there, there's carbon on both sides, we call that sulfide. Okay, sulfide, like dimethyl sulfide. These are specific compounds. We have more than that. This is just one. Lots of them. Okay, but they all share the same or very similar physical and chemical properties. That's why we call them functional group. Disulfide, just because there has 2 of them. Okay. Sulfoxide, so it's sulfide with oxygens. That's what we call sulfur oxide, which is sulfoxide. Okay, here's a popular one. Aldehyde, double bond O and hydrogens. Notice everything here. Okay, everything that's shown here. That's aldehyde, like acetaldehyde. If you don't see that hydrogen, just double bond O. That's it. Carbon on both sides. That's known as ketone, like propanol or acetone. Now if you see a double bond O and OH, that's it on one end. Nothing else. Okay? The other side just bonded to carbon or even hydrogens, like acetic acid. This will be carboxylic acid. Well, notice the difference. You don't see that hydrogen. Instead, you see a carbon. That would be ester. Okay? Notice that difference. Now, if that oxygen is replaced by sulfur, we call it thioester. As is thio is sulfur. And if that is replaced by nitrogen, we call amine. Okay, it's pretty cool. You guys see that? If you only replace one atom, you make a huge difference. You make it brand new functional groups. All right. And if that is a halogen like Cl, that will be acid chloride, because Cl is chlorine chloride. Now going back to the oxygen, and then we add another C double bond O. So that's like 2 ester. And we call that a carboxylic acid anhydride. Okay. All right. So that's all about functional group. Very special. Okay. This one is very fancy. Got a lot of C double bond O and oxygens. All right. So be able to recognize that structure or functional group and name it. Okay. Okay. Now we're going to be naming hydrocarbons, starting out with alkanes. Okay. You notice only single bond, nothing special. Okay. But they are the fundamental structure, foundation structure of all organic compounds. Okay, methane. It's a hydrocarbon with 1 carbon and 4 hydrogens. Because remember, carbon has to have 4 bonds. If you have 2 carbon, very likely they are connected together and then surrounded by hydrogens. Make sure each of them has 4 bonds. When you have 2 carbon, we save, 1 carbon we need 4, but 2 we don't need 8, okay, because we already make connection between them. So we save 2 hydrogens. We only need CH3 on each side because they share that bond right there. So that's what we save. 3 on the other side. So we save 2 hydrogen there. So that's why you only have 2 C2H6. Now 3, instead of 3 carbon, that's 12 hydrogen because 4 each. But we only need 8. Okay. All right, we save another 2. 3 carbon connect together and then surrounded by hydrogens, just to make sure carbon has 4 bonds, and so on and so on. 4, okay? Now, we can't just keep showing all the hydrogen, because that takes too much time. Therefore, we got to condense formulas. We condense them. So instead of writing CH4 hydrogen, we just write CH4. This one, for each carbon, we're just going to write CH3 on this side, and this side CH3. And then if you have the middle one, that's only 2 hydrogens. That's CH2. That's why we come up with these condensed formulas or condensed structure. Okay, like butane. Instead of, you see the connection right there, butane here. This is also butane. CH3, CH2, CH2. We condense it, CH3, so make it faster. Now you can make a bond between the group that you just condensed, a dash, or you can just write them right next to each other. Okay. Now that's butane. Now there's another way to draw the structure, another possible structure of butane. Instead of making 4 in a row, we're just going to make 3. Okay, so instead of CH2 in the middle, we want to connect what we call a substituent or a branch of that. And that will be CH3 because the carbon needs to have 4 bonds. And that doesn't need CH2 because it has additional bonds already. Okay, now overall they add up to the same number of hydrogens. Well, obviously carbons are 4, the same. Hydrogens, you add them up, still 10. this one or this one, they both have 10 hydrogens. Okay, now, but these twos are different structure because different way we arrange the atoms, different bonding sequence, straight ahead, straight chains. That's only 3 straight and 1 on top. That's a branch. Okay, by the way, these are called structural isomers. They have different structure, therefore different physical and chemical property, but same molecular formula, C4H10. Okay. Now the naming will be different. We're going to go over the naming too, but here, just to give you an idea, 1, 2, 3. If you number it 1, 2, 3, and that's what we call 2, at carbon number 2, there's a branch called methyl, CH3. So that's what we call 2-methyl propane. Okay, but propane is the hydrocarbon with 3 continuous carbons. Different functional group. These two, one is an alcohol and the other one is an ether. These are structural isomers. We're basically moving atoms around. Oxygen on the right side, move it to the middle, and therefore we have to adjust the number of hydrogens. Okay. Different positions of the functional group, like number right here in the middle carbon, or on the side, on the right or on the left. Okay. These are also known as structural isomers. So, what's our job? Be able to recognize if we have 2 or more structures. Be able to recognize how they are related. They are structural isomers. How do we do that? We inspect all atoms, number of carbons, number of hydrogens, and other type of atoms like nitrogens or oxygens or halogens. If 2 or more structure have the same number of atoms for each element, so they share the same molecular formula, 2, 3, or 4 structures share the same molecular formulas, they must be structural isomers. Okay. All right. Only different in positions. These are the 3 possible ways. Okay. Okay. Now, back to what I just mentioned earlier, the expanded versus condensed formula. We can't just keep showing all the hydrogen. So each group, carbon and hydrogen, we condense together. That's 1 carbon, 3 hydrogens, CH3. 1 carbon, 2 hydrogens, CH2. Another carbon, 2 hydrogen, CH2. So, and again, you can put the bond between them, or you can just write them close together. That's fine. Or if we want to make it quicker, we just write CH2, and that's 2 of them. We put parentheses 2. Oh yeah, we're gonna be glad if we have like 10 in the middle, 10 CH2. All we have to do is just put parentheses, put the 10, instead of writing CH2 10 times. So it's actually very convenient. Okay. All right. And remember, every time we connect something, we have to give up our hydrogens. Okay. Now here's the list of hydrocarbons, straight chain. 1 carbon, CH4, that's methane. 2 carbon, that's ethane. 3 propane, so on and so forth. Now, if we know the first 10, that should be good enough. 10 decans. And that's the formula. Okay, now we go back to the naming with branches, okay? And the rule is to start numbering the carbon and keep going to find the longest carbon chains. So we can go 1, 2, 3, 4, 5. Now if you go 5, 6, that's 1 carbon shorter. You go 5, 6, 7. Okay, so you got 7 carbon. All right. Now, any carbon that's not numbers, that will be a branch or a substituents. That's the one that's not number. It doesn't have a numbers. These two don't have numbers. Okay, this is actually a branch or a substituents. And they stick to carbon number 4. This methyl right here stick to carbon number 3. Okay, so we got 3 methyl. And we have 4, at carbon number 4, we have an ethyl. All right. We have to keep the sequence going, the longest. Now, alphabetical order. Ethyl goes before methyl, even though the methyl comes sooner, number 3. We still have to put ethyl first. That's why 4-ethyl, 3-methyl heptane, because we have a total of 7 on the main chains, 7. All right. Over here, we're just going to go straight, from right to left. 1, 2, 3, 4, 5, 6. And that's the longest carbon chains, the longest. You want to start on the side that's closer to the first branch. Okay, like 1, 2. Oh, we got a branch. But we cannot go there because that make it too short. So anything that's not number, that's not part of the main chains, is a branch. So we got a methyl here. We also get a methyl there. And on the same carbon number 4, we also get an ethyl on the bottom. Okay. Well, CH3 is known as methyl because the name comes from methane. CH2, CH3, that's 2 carbon, that's known as ethyl. That's what we have to remember. Okay. So here we got 2, 4, dimethyl, di means 2. 4, we also have a branch called ethyl. So, alphabetical order, 4-ethyl, it's got to go first, even though it comes later. 2,4-dimethylhexane, because we have the total of 6 carbon. 6 carbon, hexane. Okay. CH3, methyl. CH3, another methyl. CH2, CH3, that's ethyl. All right. The number tells us where the locations of the branch is. All right, here's more example. Now, it's good to start up here because that's make it a change longer. If you start right here, it's only 5. 1, 2, 3, 4, 5. If we start up here, 1, 2, 3, 4, 5, 6. That make this guy not belonging to the chains, but that's fine. That's a branch. CH3, that's a methyl bonded to carbon number 3. That's what we call 3-methyl hexane. 6 carbon total. So there's a lot of detail here we need to know. Okay. Now this one's a little bit more complicated, but it's not too bad. It go start from this side. 1, 2, 3. We got a branch up here. Okay. Now if we start on this side, we're gonna be 1, 2, 3 as well, but that's a methyl versus an ethyl. Ethyl go first. 4 plus the next carbon, we got a branch. Okay. 5, 6, 7. Now instead of going straight, we have to go up here, 8, 9, because we have 2 more up here. So instead of going straight and make this a branch, we need to go up here because the chain is longer and make the smaller one a branch. Just imagine, a branch has to be smaller. You can't have a branch bigger than a tree itself, and that's going to fall off, right? Okay, so that's what we got, a little longer. Little branch always better. Okay. All right, so now we got a 3, we got a 4, and we got a 7. Those are where the branches are. Well, 3 you got to go first. That's an ethyl. 3-ethyl. 4. Instead of saying 4-methyl, 7-methyl, we just combine them together, 4,7-dimethyl. It's a no name because it's got 9 carbon. All right, over here we got 1, 2, 1, 2. We got a methyl, that's close. 3, we have an ethyl. So we got 3 ethyl, 2 methyl, hexane, because we have a total of 6 carbon in the chains. Okay, that should be good enough for alkane with branches or substituents. Well, on the test, we're going to have either one, mostly it's going to be one branch, or 2 branches, okay? But 3/4 are possible, of course, like this example. Now, it's not here, but notice you also have halogens, can also be branches. Like we seen them earlier, like chlorine we call that chloro, bromine we call bromo, so on and so forth. Okay. Now cycloalkanes, these are the enclosed structure, and instead of writing CH2, okay, writing out a carbon, we just make each carbon a dot. See, you see the black dot right there? That's each carbon. This is the 3D models of the molecules. Now, this one right here has 2 hydrogens. Each carbon has 2 hydrogens, so that's each of them is a CH2, and we're just connecting the carbon dots, make a triangle, okay, and that's cyclopropane. If it's open, we call it a propane with 3 carbon, but because they're enclosed, we call that cyclopropane. Now, if it's 4, remember each carbon is a CH2 because they come around, okay? And that will be cyclobutane. If it's completely open, straight from left to right or right to left, that will be just a butane. Similarly, we have a cyclopentane, cyclohexane. So the difference is a cyclo prefix. Okay, now if we have a cyclopentane and we have a branch, we don't need to number it because there's only one branch. The structure comes around anyways, so there's no need to put number 1 on it. That's what we call methyl cyclopentane. Now, if the cyclo is smaller than the other chains, that's 1, 2, 3, 4, that's a regular butane. In that case, we do need to number because that's the straight chains. And we treat this as a branch. So that's why in case this is number 1 right here. It's not, it doesn't show here, but it's number 1. And that's 1 cyclopropyl instead of cyclopropane, cyclopropyl, because we treat this as a branch. And we treat this as the main alkane, which is butane. 1 cyclopropyl butane. Okay, now if we have 2 or more branches, we have the numbers to tell the difference. Now we put number 1 on the ethyl. Remember CH2, CH3 is ethyl. CH3 is methyl. We don't want to put number 1 there because ethyl go first, alphabetical order. If we have a choice, we put 1 for the ethyl because we want to put ethyl first. Okay, on a straight chain, sometimes we don't have a choice. We have to put whatever, methyl first. But we still have to name ethyl first because alphabetical order. Okay. But here we do have a choice. So we put 1, and that make it 1 ethyl, 2 methyl, cyclopentane. All right. All right, let's practice. How will we name this? Okay. And please write it down somewhere. We got a propyl. That's 3 carbon. That's propane, but we call it propyl. And we have CH3. That's methyl. Methyl and propyl. I believe methyl go first. Alphabetical order M. So we put number 1 right here. 1, 2, 3. You don't want to go this way because 1, 2, 3, 4. That's 1 step further. You want closer. Okay. So that's 1 methyl, 3 propyl, cyclopentane. 1 dash methyl, 3 dash propyl cyclopentane. Okay. Now this one, it doesn't matter which way you go. 1, 2, 3, 4. 1, 2, 3, 4. It's the same numbering. And these two are the same branches. They're both methyl. So we're going to call 1, 4 dimethyl cyclohexane. Again, that's 1, 4 dash dimethyl cyclohexane. Okay, so that's alkane, only single bond. How about alkenes? Okay, double bond. Now, that's a functional group. That's a class name. Alkane doesn't have anything special, right? It's a fundamental though, foundation molecules though. Now, we got a double bond, and we have the number closer on the side that's closer to the double bond because it's a class. Okay, nothing else matters right now. If you have a branch closer on the other side, you still go with a double bond. That's because it's a class. The class is higher than a branch. Okay, and we got, that's why we have 1, 2, 3, 4, 5, 6. Okay, the first carbon of the double bond, that's what we have to label. 2-hexene, only the first one. All right, over here, we can go on this side 1, 2, 3, or 1, 2, 3. We reach the double bond the same distance. But however, on the left side, we got a branch. In that case, we're going to go on the left side. Okay? All right. Now that's 1, 2, so we got 2 methyl. 3, remember, first carbon of the double bond, 3, hexene. Hex because it has 6 total. All right, look at this one. When you see double bond, automatically that's number 1. I know that's going to be longer. You can go 1, 2, 3, 4, 5, 6. But that does not include the double bond. So we have to go start with the double bond. And that's going to be the first carbon of the double bond. And that's go right there, 1 pentene. And 2, we have an ethyl branch. Okay, 2 ethyl, 1 pentene. Obviously, this one, if we have a 2 double bond, you're not responsible for 2 double bond. For the introductory chemistry class, we're not responsible for multiple double bond. But it's kind of nice to know as an options. We got 2 double bonds, so 1 and 3. Remember, only the first carbon of the double bond. That has to be addressed. Okay, 1, 3. So, and we got 2 methyl branch. So that's 2 methyl, 1, 3, butadiene. It's a butane, it's a diene, 2 double bond. 1, 3, butadiene. And we also, just like alkane, we also have cyclo. Okay, cycloalkene in this case with double bond. Now, and the reason why we have to number, if you don't have a branch, you don't have to number it because we have a branch. Now we have a double bond and a branch. That's more than one thing. We have to number it. And that's going to be 1 methyl cyclohexene. Notice we don't have to call it 1 cyclohexene because it's part of the ring. And automatically number 1. Now you have 2, again, for intro class, we're not responsible, but it's nice to know. 1, 2, 3, 4, only the first carbon, 1, 4, cyclohexadiene. Now this one, we're responsible for this one, 1, 2. Notice we can't go that way because we have to include the double bond. And that's number 1 because it has a branch as well. So we have to go this way. We have no choice. 1, 2, 3, 4, 5. And that's why we end up with 1, 5 dimethyl cyclopentene. Okay. All right. This will make it easy for us. This is 1, 2, 1, 2, 1, 2, 3, 4, 5, 6. So that's cyclohexene. So 1, 2 di, 1 comma 2 dash dimethyl cyclohexene. Okay. There are two different possible ways to show an alkene in 3D, and that's make it a cis versus a trans. And you probably heard about cis trans fat. Okay, trans fat is not as good as cis. I mean, unsaturated fat's already good, better than a saturated one, but the cis is better because they don't get stored in the body very well. They get metabolized and used for energy and out. We don't want to store too many fat molecules, just enough for reserve. Okay. Now this one is a cis because if you notice in space, the two metals are on the same side, upper side or lower side, left side or right side. As long as they're on the same side, we call that a cis. Now you also look at the hydrogen if they are there on the same side. That's a cis. 2-butene. Now a trans is this one when they're opposite. Transoceans opposite. You also can look at the two hydrogens as well. Okay, so people to recognize cis versus trans, and that's good enough. Okay, now we're gonna stop right here, and in the next video we'll be looking at reaction of alkenes and alkanes, and also move on to the last two type of hydrocarbon that will be alkyne with triple bond and aromatic compounds. Okay, all right. Thank you guys, and we'll see you in the next video.